Okay, and the co-chair is Thierry Schneider, and there are two rapporteurs, Aidana Amrenova and Fredo Zolzer. So Thierry?
Yes.
Thank you. So my name is Thierry Schneider. I am also member of the main commission and chair of Committee 4. I'm the director of CEPN, which is Nuclear Protection Evaluation Center in France, specialist of post-accident ethics and optimization, more or less. Then I am involved in this TG to really bring some reflection on what could be the consequence on the implementation, because Committee 4 is dedicated to discussing implementation of international recommendation. And so it's why I will show you some few elements tomorrow on the preliminary reflection on this topic.
So I'm Augusto Giussani. I work at BFS. I'm internal dosimetrist. I'm the leader of the group External and Internal Dosimetry Biokinetics. I'm member of Committee 2 of ICRP, and I chair the task group on radiopharmaceuticals. And in these task groups, task group, I will coordinate, consider the issues of dosimetry for effects for the exposure during pregnancy and before pregnancy and for the offspring.
I'm Niranjan. I'm from Karlsruhe Institute of Technology. I'm doing my PhD work on biokinetic and dosimetric models for americium, and then later I'll be doing the biokinetic modeling of DTPA.
So good afternoon. I'm Aidana Amrenova. I'm a postdoc at the IRSN in France, and also a mentee of TG121. And now I'm doing the systematic review on heritable effects in offspring and next generations.
Yeah, hello, I'm Peter Scholz-Kreisel. I'm also from the BFS, and I'm a biologist and epidemiologist by training, and I'm head of the section Radiation Epidemiology and Risk Assessment at the BFS. I'm not a member of the ICRP, but just a guest today. My main focus is on late effects of therapy, radiation therapy, and long-term effects of radiation.
Thank you. My name is Werner Rühm. I'm from the Helmholtz Center in Munich. I'm not a member of this task group. I'm not a member of Committee 4, neither of Committee 1. And currently I'm serving as the chair of ICRP, and I just want to learn from you what the potential impacts are.
So can we continue the presentation of everybody online? So who can be the first? Fredo?
Yes, I'm Fredo Zolzer. I'm at the University of South Bohemia in the Czech Republic. I'm sorry, I'm online. I wanted to come be there physically, but was prevented by a common cold, as you say. I'm a member of Committee 4, and I was a member of the task group on ethics of the system of radiological protection, and now I'm a member of the task group on the ethics of medical applications of radiation. So ethics is one of my focus areas, but I'm a radiobiologist by trade. And there's one more person online, I think, Geraldine.
Yeah. Good afternoon. Can you hear me?
Yeah.
Yeah. Okay. Good afternoon. My name is Geraldine O'Reilly. I'm a medical physicist working in a large teaching hospital in Dublin. I'm a member of the Article 31 group of experts that advise the European Commission. So I would have been involved in the drafting of the European BSS and I'm currently chairing the working party to that group that look at medical exposures. So I hope to be involved in the drafting of the next iteration of the BSS. So I'm here as a guest today. So thank you for the invitation to participate. Thank you.
So thank you for being online. Are there other people online? Only the two of them?
Yeah, only two. We see only two.
Yeah. Okay, so we are missing Pedro Vaz and Radu Vazilash and Liz Ainsbury, but I don't know, maybe they will. I have to check my emails maybe, but I hope they will connect tomorrow. And so if we come back to the so the idea is to, the idea for our group is to discuss about the introduction and the impact of heritable effects and exposure of in utero exposure to radiation for the system of radiological protection. So with effects of in utero, effects of heritable effects, and also the potential impact of heritable effects for non-human biota. So to consider all these different impacts on the current radiation protection system. And for this, we have three presentations that are scheduled in the group D. The first one by Aidana is about how heritable effects were quantified in ICRP publication 103 in the detriment. The second one by Thierry Schneider will be addressing heritable effects in the implementation of the system of radiological protection. And the third one by Frido Zolzer will be about ethical aspects of radiological protection for spring and the next generations. So that's the first point is very different from the two others. The proposal we had was to begin with the presentation by Aidana Amrenova today and to discuss about the aspects, quantitative aspects of how we have to integrate scientific elements in the construction of the detriments. And to have the two other presentation move to tomorrow to begin with that for the tomorrow session and to come back for more general presentations. So if everybody agrees, I propose that we move to the presentation by Aidana. Oh no, before that, you also received a list of questions that are listed there. So question one is compared to the state of knowledge in 2007, what is the contribution of new scientific knowledge on how to consider preconceptional effects of exposure to ionizing radiation in the assessment of risk in humans in support to radiological protection system? And so clearly this question is how to take into account elements that will be discussed in the next days by group A, B, and group A mainly. But for us, the question is what are the types of effects? Are there variations in the baseline rates? On how many generations? How to weight by severity? Do we have to weight by severity in the same way as for cancer? And how to extrapolate from experimental results to humans? At least we can review how it has been done in the ICRP system right now. Question 3 and 4 are the same, but for in utero exposure. And here the questions are consideration of cancer in the detriment, which is not done at the time being, weighting by severity, and classification of effects that are considered as tissue reactions at the time being in the system. And the next questions, question 5 is about non-human biota. So what are the dose ranges, the types of effects, how many generations? But again, it's difficult to discuss without members of Group C. And the last questions are what changes are expected in the classification and quantification of effects regarding preconceptional and post-conceptional effects in humans? What is the potential effects in the system of radiological protection? Question 7, how to better consider the effects of in utero exposure in the radiological protection in the medical field. And 8, how to better consider ethical and societal aspects related to effects of exposure to ionizing radiation on offspring and next generation. So I think that for the discussion tomorrow, we can extend the question 7 and 8. That will be the most of the focus of the question for tomorrow. And question 1 to 4 will be directly related to the presentation of Aidana right now. That's it for the introduction. So if there are no questions, I propose we move to the presentation by Aidana, how it is considered at the time being in the system, and we begin with the first questions. Aidana, is it okay?
So. Yes. Could you give me No. Yes, sure.
It was the one that was.
Okay, thank you, Dominic, for the introduction. And today I'm going to talk about how heritable effects were quantified in ICRP publication 103. Thanks. Okay. So about the doubling dose method and how the risk were quantified, the components and the estimates of genetic risks. So exposure to ionizing radiation results in an increase in the frequency of germline mutations over and above that occurring spontaneously. And these observations and the concern that radiation exposure of human populations might cause a genetic disease in the descendants of those exposed dictated the need to develop methods to estimate the genetic risk associated with radiation exposure. And in the absence of human data on radiation-induced genetic disease, all the methods are indirect. It means from mice model. And the aim of this method is to make the best use of mutation data to predict the radiation risk of genetic disease in humans. And one of such methods that has been used from the early 1970s until now is the doubling dose method. Doubling dose method is based on the equilibrium theory, which is population genetics used to explain the dynamics of a mutant gene in a population. And with the doubling dose method, risk per unit dose is expressed as a product of 4 quantities. The baseline, the baseline frequency, the doubling dose, mutation component, and potential recoverability correction factor. Until 1980s, the risk per unit dose was calculated using only baseline frequency and the doubling dose, and the concept of a mutation component was formulated in 1972, but was discussed in task group, ICRP task group, and it's included to the equilibrium in from 1993, and the last component was potential recoverability correction factor. So I would like briefly discuss all the components for this equilibrium. Yes. Baseline frequency or initial incidence of disease class under the study. It does the Mendelian, including autosomal dominant, X-linked, autosomal recessive, chromosomal, and multifactorial, including chronic disease and congenital abnormalities. And the baseline frequency based on the data from Carter, Anscare reports, Zeisel, and Sankaranarian. Compared to the estimates used in the 1993 Anscare report, the total incidence for Mendelian disease have been revised, and recent estimates suggest that about 2.4% of all live births suffered from one or another of Mendelian disease. Yes, yes.
Chronic disease is including cancer, cardiovascular disease,
Yes.
During life.
During life.
Approximately 1/3 will have cancer, 1/3 will have cardiovascular disease, and but no, come back to that. Yeah. But clearly that's something which is really surprising. That's all kind of these, finally all kind of diseases are considered here as something that can be transmitted in the baseline rate, which is very surprising. And it makes a huge discrepancy between this line and the other ones, which are 0 point something. But so when we are speaking about, that's the first point. When we are speaking about any table effects, we are speaking about a list of. No, please continue. That's part of the discussion. We will come back.
Okay. Next is a doubling dose, and doubling dose is defined as the amount of radiation that is required to produce as many mutations as those that occur spontaneously in a generation. And the concept was formulated by Müller in 1950, and the conceptual basis and database used for estimating doubling dose have been fluctuated over the years. The doubling dose is calculated on the basis of rates of spontaneous mutation and induced mutation at defined gene loci, and from 1977 till the 1993, the Berry Committee and Tasquet used the mouse data on both spontaneous and induced race mutation to calculate the doubling dose with the one assumption that the spontaneous and induced mutation rates in mice and humans are the same. And the doubling dose was equal to 1 gray, but the mouse, the spontaneous mutation in mouse humans is not the same. So after that, I decided to use the human data on rates of spontaneous mutation and mouse data on rates of induced recessive mutation, but with the assumption that the average rate of induction of mutation in human germ cells was the same as that in mouse germ cells. And here you can see the doubling dose. It's 0.82, which is not so different from 1 gray, and they decided to keep using the 1 gray. So next is the mutation component, and mutation component provides us a measure of how the disease frequency will increase and the mutation rate is increased. And the main reason of having this quantity in the risk equation is that the relationship between mutation and disease varies between different classes of genetic disease, and which is easy to calculate for autosomal dominant and X-linked, and difficult to autosomal recessive, and very complex for chronic multifactorial disease. And at the end, mutation component for autosomal dominant and X-linked is 0.3 and close to 0 for autosomal recessive, and about 1.01 to 1.02 for chronic multifactorial disease. As I told you previously, the doubling dose was calculated on the basis of data of induced mutation rate from the mouse data, but it's not appropriate of use the induced rate of mutation in a limited number of mouse genes for estimating the risk of inducible genetic disease in human. But since there is no alternative to use the mouse radiation data for risk estimation, there is no need to bridge the gap between the rates of induced mutation in mice and those of induced mutation that are potentially recoverable in human. And one of the approach was to introduce the disease class specific correction factor, which is called potential recoverability correction factor. And in order to estimate PRCF, certain criteria for potential recoverability of induced mutation in human live birth were defined on the basis of molecularly analyzed mutation in experimental system. If shortly, a total of 63 human genes was included in the analysis. Only in 21 or in 1/3 of the genes induced mutations may be compatible with viability and potentially recoverable in live birth. And the fraction about 0.3 is called unweighted factor, and the weighted factor became 0.15. So the next one. No, next slide. Yes. And finally, the estimates of genetic risk, and the risk of for example, autosomal dominant and X-linked disease is of the order of 750 to 1,500 cases per million progeny per gray of chronic radiation, and for the first generation, and 0 for autosomal recessive, and for multifactorial, for example, from 250 to 1,200, and the total risk is 0.41 to 0.64% of the baseline risk of 738,000 per million live birth, and it's at low doses of radiation of interest in risk estimation. The risk of adverse hereditary effect is small. So here the nominal risk. For example, this is from the publication 013. This was in ICP publication 60, and we can see that it's decreased. So on the basis of UNSCARE 2001, the Commission has for the first time been able to provide ICRP estimates of risks for all classes of genetic disease. And the new approach of to heritable risks continues to be based on the concept of the doubling dose for disease-associated mutations used in publication 60, but the methodology differs in the recoverability of mutations in live birth is allowed for the estimation of the doubling dose. And the Commission also notes reports which argued that the basis of above survivors and mouse genetic data that the risk of heritable diseases tended to be overestimated in the past, and also for the first time a scientifically justified method for the estimation of risk of multifactorial disease has been included, and the mouse studies continue to be used to estimate genetic risks because of the lack of clear evidence in humans that germline mutations caused by radiation result in a demonstrable genetic effect in offspring. So. And yeah, thank you for your attention. And I would like to thank, grateful for Ludovic from the CPN who helped me to understand the basic concepts and how it was calculated in publication 0103. Yes, thank you.
So is it clear now for everybody how it has been calculated?
The number of generations are different. So the number of generations was different in ICRP 60 and ICRP 103. So 103 was 2 generations, and 60, how many? 10. And what was the reason that they changed it? Do you know that?
Yes, you're right. In ICRP 16, it was up to 10 generations, and they decided to keep the only 2, and they just thought it's maybe reasonable, and there is no effect in other generations. Yes, but yeah, that's also a question to discuss during these 3 days.
So maybe it's just an interpretation. The ICRP 16 10 generation were practically only animal studies. And probably in 103, you had also some human studies, which you know. Okay, so it's right. But because of the difference is quite remarkable for the risk factor. Mm-hmm.
As far as I understood, it was the recommendation by OnScare that considering 2 generations was more accurate and sort of with less uncertainty and enough to reflect the impact of exposure for the offspring. And finally, the decision was to use that by ICRP. After that, it's not the only change. So there have been many different changes in the way it was calculated. So it's not only due to the reduction of the generations, the change between the ICRP 60 and ICRP 103, but clearly that's one of the questions that we have to ask ourselves. Do we have to increase? Is it still logical to limit to 2 generations? And from what the the presentation we saw this morning, clearly, if we stop at 2 generations, we are not really considering the transgenerational effects, at least in the presentation by Zdenko.
Yeah, there are some explanation for the selection of 2 generations in publication 103. I think it came from OnScare 2001 and also National Academy of Science and NRC 2006. And it was considered at that time by ICRP that finally the type of effect were considered was mainly during the first 2 generations. But then maybe if we consider different type of effect, as you mentioned, we can come back on this consideration. And then the conclusion, I just read what have been selected on ICRP publication 103. It was judged by ICRP that expressing genetic risk up to the second generation will not lead to any substantial underestimate of the heritable effect of radiation. So that was based on there are different considerations. We can come back in detail, but that was a justification which was provided at the time for selecting only two generations compared to 10 previously. Then is it still justified or not? This is a matter of discussion, but that was mainly based on UNSCARE and NRC report.
No, because UNSCARE is currently not working on that. We cannot blame UNSCARE in the future for any decision, right? So it's this task group.
Other questions? Can you come back to the equation? Not to the slides, but to a previous one. No. No. Oh, yeah, I think we don't need the questions really. Yeah. Yeah. Okay. So to come back to the discussion we had this morning, here you have four different things. Only one is really dealing with radiation. Is that it? The dose, the doubling dose. And so the first point is that the doubling dose is coming only from animal experiments. There's nothing from human, which makes it very different from the other elements that are in the detriment. All the rest is coming from humans. Partly.
For calculation, they use ratio of spontaneous mutation from human data. Yes, and induced from mouse.
But outside of heritable effects, everything is coming from humans for in the detriment from the LSS mainly, but for cancer, it's coming from epidemiological studies. And so the doubling dose is also not really linear, because it's the dose that makes it double from the spontaneous rate, and so it's in the detriment, but without any support for the LNT or for the absence of a threshold. It's just the dose that makes double of the baseline rates, which is a very crude approach compared to a model of dose risk relationship. That's only one point. It's much closer to what is done in the chemical field, for example. the baseline frequency. So it's coming from, so I don't know, but maybe it has to be updated from 1990. I think today we have a much better, so baseline frequency is really from human, but I'm not sure that today we don't have a much better baseline frequency of heritable effects of genetic disease, let's say, than compared to the 90s. So maybe that's something that could be revised, updated, let's say, like we are going to do for the baseline rates of cancer. And from what I understood this in the morning, in fact, there has been some changes because 20 years ago, we were considering, let's say, I don't know, a few tens of genes. And today we are able to consider thousands of genes, which makes it different in the baseline rates. The mutation component is so, but at least these two ones are based on science, in my view. The doubling dose is coming from experiments, and the baseline frequency is coming from statistics. Mutation component, in my view, is much more an expert advice, and it's even more true for the PRCF. I'm still not sure I understand the PRCF. Can you come back to the mutation component and PRCF? Or do you have also questions about these different elements? But
so just to understand, so the issue of the first part is that one, the concept of the doubling dose is a little bit a deviation from the linear non-threshold.
Yeah, something
completely different, and it's based on animal differently from the other one. So it's, yeah. That was the next question. Yeah, which is the dose and which is the uncertainty then to the mouse. Okay.
Yeah, coming back to this equation, I have the feeling that with what we heard this morning, one first element will be to clarify which type of, is it disease or mutation or effect we can consider, because it's not sure that what we had in publication 103 still correspond to all the knowledge that we have now. It's not sure because in your presentation, Aidana, you had genetic effect, hereditary effect, and then we heard this morning so many different categories of effects. So what is encapsulated into the calculation of the detriment? We say genetic effect or hereditary effect. Not sure. We have nothing with regard to in utero exposure or not, or preconceptual aspects. So how to embark to be sure that we have all the categories of disease or impact, and then which impact may be considered as a disease, because it's not so clear, and especially if you consider the thousands of genes, some of them can be observed, but without significant impact on individual, possibly on population. But then how to deal with that? It's not so clear. So of course we need to have the feedback from the other group on this topic, but that will be a significant concern to see if this equation is still valid, or if we need to expand some element.
What I understood from this equation is that P is the baseline frequency of genetic disease. The doubling dose is for genetic mutation. That's the doubling dose. That's the dose that makes double the frequency of mutation. and from this mutation to the disease, it's the MC. That's what I understood. If you can show the slide on MC. Yeah. Thank you. So MC provides a measure of how the disease frequency will increase when the mutation rate is increased. So DD is corresponding to an increase in the mutation rate. But to go from the mutation rate to the disease, they applied this coefficient, which is 0.3 for autosomal dominant, 0 for autosomal recessive, and 0.01 to 0.02 for chronic multifactorial disease, including 65% of the diseases in a population. So you can have whatever you want as a DD. If you multiply by 0 or by 0.01, you are sure that you're not going to have a large quantity in the end. And this, I don't know. I tried, so I did not read the NSCARE report in details and so on. But reading the ICRP 103, there's no scientific support for that. So in my view, these coefficients are much more expert advice than scientifically based. And in this equation, it's not clear, in my view, that it's a clear mix of things that are scientifically based and things that are kind of expert advice. So I would be interested in knowing if there is a possibility to have the uncertainty associated to these three coefficients. It should be several hundreds of percent for sure. Fredo, you were asking for the...
Yeah, thank you. I didn't know if you saw my hand. I was surprised by the statement of Aidana that it is not the doubling dose itself which is assumed to be the same between humans and animals, but it is the rate of induction. So did I understand that correctly? Then it means that the rate of induction is the baseline plus the doubling or combined with the doubling dose, which is supposed to be the same. And the doubling dose itself is different in humans than in animals, or is assumed to be different. Is that correct? Or did I totally misunderstand this?
So could you please repeat your question, because I don't understand. You're asking how the doubling dose was calculated, like which kind of data was?
No, you said that the rate of induction of mutations per dose is assumed to be the same in humans and in animals, and that would mean, I think, that the doubling dose is different because the background frequency is different. I'm just trying to check if my understanding is correct. Maybe I should look at the text itself, but...
Yeah. To go back to the slide. What I understood, Fredo, from that is that the doubling dose is estimated from mice. In the experiments, they know what is the rate, the spontaneous rate of mutation in non-exposed animals. And they can see that in animals exposed by 1 gray, they can have twice the number of mutation.
Yes.
So and so that this is from animals, but to apply it to humans, they made the assumption that the doubling dose is the same, but that it has to be applied to the baseline rate in humans, which is very different from mice.
So then, in that case, sorry.
And so they took the baseline rates from the human population and they multiplied it by the doubling dose derived from the mice. So a very strong hypothesis is that the doubling dose is the same in mice and in humans.
Okay, this is what I understood until now, but I think, well, maybe I misheard this, but I think I heard the statement that the rate of induction is the same in animals and humans. And that's different. The doubling dose is the same. That's different from the rate of induction is the same, because the doubling dose refers to the baseline frequency.
No, they just make an assumption that the induced mutation rate in mouse and human are the same. And they use this this assumption to, on the basis of this assumption, they calculated the doubling dose.
Okay, and we'll do some more reading tonight, I think. I still don't understand it.
This one. Yes. Yeah, the doubling dose was calculated on the basis of human data on rates of spontaneous mutation and mouse data on the rates of induced mutation at defined gene loci. But they made an assumption that the average rate of induction mutation in human germ cells was the same as that in mouse germ cells, if you are talking about that.
So I don't want to prolong the discussion. I have to get it clear by some home study, homework.
So, like, I feel this assumption should not be like, this shouldn't be correct. They should, like, in the human body is more complex, or say it has more cells. So this assumption, if you are using this assumption, then I think our lot of data will be wrong.
Yeah. Yeah, they. Yes, you're right, because for the induction mutation, they don't have data from the human germ cells. That's why they decided to keep using the data from the mouse germ cells, but they made this assumption like they are same. Of course, they are not, but there's no any data. And if you back to the ANSCARE report until the 1993, they use for calculating of the doubling dose, they use the mouse data on both spontaneous and induced mutation, but there are human data on the spontaneous mutation, and as you told, the human and mouse organisms are totally different, especially the lifespan of the mouse is shorter compared to the human, and the spermatogenesis also, and that's why they thought that it's more reasonable to use the human data on spontaneous and keep using the mouse data on induced mutation.
Below, is it better now? Or? Yes, we can circulate publication 103 for tonight, and the annex on heritable effects is already sent. We can have a look at that for sure. And so to come back, so this MC, the mutation, the MC coefficient, in my view, very, and I also know we can get expected. That's the reason why the new position has been opened for somebody who is finally is not related to radiation. This coefficient is not related to radiation. That's just all disease is related to mutation rates. So that's very, but clearly the uncertainty about that is very strong. So maybe we don't need to have DD very precise because anyway we reply by something which is highly precise. And it's even worse for the last one. So can we move from my one slide? This one, can you try to explain it again? That's still not sure I understand it.
Me too. I don't understand it so deeply. But as we discussed about the induced mutation, and as I told, there is no human data on induced mutation. So we decided to bridge the gap between the rates of induced mutation in mouse and human. And they decided to use the potential recoverability correction factor. And there are some calculation, the analysis they made, and this potential recoverability correction factor divided into unweighted, which is equal to 0.3, and weighted, which is equal 0.15. But I don't understand clearly why they decided to include the weighted and unweighted factor. Yeah.
Again, whatever the weight, it's only actually again 0.3, and finally decided to go to 0.15. So again, that's in my view more an expert advice than which is really scientifically based. That's a kind of weighting coefficient, but and what I understood is that from discussion with Ludovic was that this coefficient was intended to move the results from mice to humans, and to consider that in humans. Finally, many mutations will not be viable or repaired, or I don't know, but with no impact afterward compared to mice, and so that it was another estimation to use the results directly from mice, and that it has to be weighted down to be applied to humans. But multiplying by 0.15 is clearly a very strong impact in the results.
Just to get it clear, I'm a bit humbled now. When changing the DD from 1 gray to 0.83 gray, the assumed risk or impact is calculated larger because of the transfer of the risk to humans. But then, due to the transfer of the risk to humans, they add an additional factor which is correcting it down again. So at the first factor, we are calculating it up, and the second, we calculate it down. But
for the 3 parameters, because what is in the equation is 1 divided by d. So 1 is 1 instead of 0.8.
no, it's 1 by 1 0.
Divided by 1.
Yeah,
So 1 divided
the 1. 1 by divided by 1 is 1, and it's not a problem. Exactly, it's a problem.
May I have a question, Dominique? I mean, you said that this is a different concept than the LNT or dose response concept we have. So should this be one of the questions we have to the other groups, whether there is any chance to get a dose response relationship, be it linear or whatsoever, on this type of endpoints for animals, for mice? Yeah, of course. So, I mean, this would be a very important information. If they say, no, there is nothing, there's no way, even 20 years later, then we should continue with this DD, doubling dose concept. If they say, well, maybe there is something among Drosophila, or I don't know, something we could think about or check the influence if we change the concept here. So this is one question I would ask to the other groups.
I think what we have to do to the other group, to group A, in fact, is to ask for the four parameters that are in. Do we have new estimates of the frequency of mutation in a human population? Do we have information about variation between different groups of population? Because I think the mutation rate should not be the same in Asian population and Caucasian population. Maybe we have enough information today. Maybe it's not worthwhile, because when you look at the other parameters, maybe that's a lot of time. For DD, I fully agree with you. Is it possible to have a better DD today, or to remove this DD and to have a model? Or do we have a neat idea of existence of a threshold? Because that's and for the two other parameters, do we have better today? That's and for the last one, if it's the idea is to transfer from animals to humans, if you compare with what is used in the chemical field, that's very different. In general, it's what is used is the upper value of the estimate to transfer to, well, so some protective parameters, you know, so some. But in that case, they make the assumption that there is a linear extrapolation between this NOEL and lower level of observed effect to zero, yes, which is not really the case here. Maybe a little bit, because finally you apply it after that to lower doses, and that the assumption is that, but.
These two factors were introduced by ICRP, or are they also taken from the UNSCEAR? These expert judgments factors.
Yes, the mutation component was introduced also not by ICRP, but it was discussed from the 1972 in Bayer reports, and the potential recoverability correction factor from the 103. Yes. Because before, for mutation component, it was like the concept, they just discussed about the concept, but in 1993, they discussed about methods, how to calculate it mathematically, and so on. And after they make a decision and make like 0.3 and so on, they have some numbers, they decided to include it to the report. Yeah.
Yeah, I have one question of clarification, because for the weighted factor, in fact, it seems it has been initially produced by UNSCEAR. Currently, we have no new value from UNSCEAR on this topic, as far as I know. So what to do? And initially, from UNSCEAR, it seems that they derive that based on the number of genes which were altered. And so if I understood correctly this morning, we had better knowledge about that now. So what could be the need for reassessment? But finally, if we reassess to say, okay, instead of 0.15, it will be 0.16 or 0.12, we don't care too much. We have to check what will be the uncertainty and the significant change on these weighting factors. And in which way there is a need to recalculate or not, and notably based on the evolution of the knowledge on this table, first on the type of heritable effect, and secondly on what we know about human data on background data, not associated with radiation, but what we know with evolution of mutation from human. Do we have additional data or not? This morning we had not too much, not really information on the baseline data from mutation, so that should be good to see, because for cancer we know that we may have incidence data. For mutation, I have no idea about that. And you mentioned also the possible differences according to the population. If you embark the epigenetic as well, how to deal with that and how far we can go. Maybe this is something for the future, and we say, okay, currently we have knowledge and we are able to derive some, to assess the detriment only for this type of disease or according to this type of information. But it's better to know what is available and in which way we can reassess some element or not.
Yeah, but maybe one thing we can try is to go the same way as cancer, and because what we have happened in the last 20 years is that we have new registers on autosomal genetic diseases, and that maybe we can get incidence numbers on that now, what wasn't available 20 years ago. So maybe we can think on this way for a baseline risk, for baseline incidence. But yeah, it's not easy, but maybe.
No, but I agree. The question is, do we have to do that? For example, for congenital malformation, there are plenty of registries all over the world today. So I think we can have different estimates for different types of congenital malformation in different parts of the world. The problem is it needed to go in more details on that part if the other ones are completely just an estimate? But at least I think it should be written. Reading the ICRP 103, it's not clearly written what is science-based and where are the uncertainties and what is just expert judgment. And to come back to the question just before, I have to check, but I think the final value of 0.2 is provided by the n-scale. So the final result of the equation for the 4 different categories of disease was of course, in that case, the coefficients, the 4 coefficients were also provided by the n-scale. It does not mean it cannot be revised today, but everything was provided by the n-scale. That's what I understood by my reading, which is only part of the science. Also, a question for you, Werner. As far as I understood, there is in addition, so it does not appear in your slides, but for the doubling dose, I think there was a dose rate reduction factor of 3 that was applied when you want to apply it to chronic exposure. Do you remember that? So in addition to what is written here, they apply also a coefficient of a division by 3, just to consider that at chronic or low dose exposure, the effect will be less than acute exposure. What is this value of 3 scientifically based or not? When I listened to that, I thought about TG91. Did you consider dead ref for heritable effects? I don't know. We have to check, but it seems that there is something, a kind of application of a reduction factor for those rates for heritable effects. I don't know what is the scientific basis for that. Do you remember that, or do you want to say something about that? Maybe tomorrow.
Sorry.
Yes, Frido, please.
Yeah, no, I didn't want to speak about that point, but about the point that you raised before, that maybe different populations around the world are different. The ICRP is supposed to make recommendations for everybody around the world. And I guess most of the data that we have is for, I don't know, North American, European populations. Would it make sense to ask for data from different parts of the world and see if there is huge variation in the baseline risks of genetic diseases, in the mutation component, in the potential recoverability factors? There could be huge differences. At least one should maybe try and have a look and put data together, how far the assumptions made so far are globally applicable. Or is that too much to ask? Probably.
I don't know, because in fact, what we are doing now is to discuss about issues, and clearly we in the room we don't have the answers. That's what I think. That for that part, at least, what we can do is to list all the questions that we raised, and for DD, for example, to ask them: is it today possible to move from the one estimate, which is the doubling dose, to something which is more corresponding to those effect model? Do we have information about the variation of P between different population? Do we have well, all the questions? We can make a list of that, and again, as has been said by André this morning, sorry, the idea is to have papers from the workshop. And so we are going to have to write something from our discussion now. But I think that part of it can be the list of questions that we have when we look at how it has been done in publication 103. And maybe some of the questions we can send it to NSCARE also. So. Yeah. No, before in the current one. Yes, the overarching report is including heritable effects, and that's one of the reasons why Anna stopped saying that it was a non-cancer, because heritable effects includes cancer. That's in the chronic diseases. It's 65% of the population, but half of it is cancer. So, which is not non-cancer because it's cancer. So we are close to that. And can you come? What is so estimates of risk here is 0.4 for the first generation, 0.4 to 0.6. Risk per gray per million, and for the second generation 0.16 to 0.4. So I think we have to sum both of them, that's it, to end up with the value which is on your next slide. And this is moved to percent per gray, which is yeah, I don't know. That's yeah. So it's clearly it's very complicated. It's including a very large diversity of different effects. Some of them are in the first years of life. Some of them are over the whole life. So that's really a very complex indicator. And another point I wanted to raise also on the previous slide is that finally it's zero in the detriment. In the end, it's a 0.2 for a total detriment of 5.7, which is 4%. No, zero. No, in ICRP 103, no, there are two columns. Present is ICRP 103. Yeah. And so it's 0.2 and 5.5 for cancer. So it's 0.2 divided by 5.7, it's 4%. So finally, we are discussing 3 days on something which represents only 4% of the detriment. So we have to be careful also, because even if we double it, it will still be a very small proportion in the detriment, at least in the way it is calculated right now. And it was much higher in ICRP 60. It was 1.3 for 7.3. It was closer to 18%. So there has been a very strong decrease, but it's written in the ICRP that between 1990 and 2001, the results have been that heritable effects were overestimated in the past. So it has been by purpose that they decrease it. I think it's not only the number of generation, but more than that. But again, we have to read it in much more detail, I guess.
Yeah, can I just confirm, or not confirm, how do you say, support that? I think the ICRP would have to reassess this contribution to the detriment. Maybe it will come to the same conclusion, but I think the justification is very weak. The justification is just we feel that it should be that, but there are no, as far as I see, maybe I'm wrong, but as far as I see, there are no arguments put forward why it should be 1.3 in ICRP 60 and 0.2 in ICRP 103. I think it's very much, even the Commission has used this wording a lot. The Commission feels that it should be this, or the Commission judges that it should be this, and no further argument is given. So I think that's a bit weak and should be reconsidered.
Yeah, I fully agree with you, Fredo. Looking in detail to the detriment, I think it's not fair to present it as one of the lines. It has been calculated completely differently. The uncertainty is huge compared to the risk for cancer, and so at least I think for transparency, or I don't know, it should not be presented in the same table. Another point that we did not discuss is that this calculation is for nominal risk. I have no slides for that. And after that, you have these 3 parameters for severity, which are loss of years of life lost, quality of life, and lethality. And as far as I understood up to now, the coefficients that have been applied are the same as for cancer, but these coefficients were not calculated for Mendelian disease or for congenital abnormalities. It was, yes, I think so. I can check for tomorrow.
Thank you. Yeah, one point which could be useful because in fact we check that between publication 60 and publication 103 we have a significant difference in terms of calculation. I'm not so sure how far the assumption or was made by ICRP or mainly by unscare. So that should be good to see according to the evolution from publication 60 to publication 103, and most of the factors that we have in the equation rely on unscare publication, and most of them, if not all, are available in unscare 2001. So what have been done, what have been assumed by ICRP, what has been just used as evolution of knowledge published by unscare. Even if unscare, I've made assumption, but this was not made by ICRP. So this is something to clarify and because if we move from the publication 103, then we need to explain why we move from publication 103, and if it is to come back on assumption from ICRP, or it is based on evolution from unscare, or if it is based on new knowledge and so on. So it should be good to start to understand why in publication 103 we have this value of 0.2 compared to the values that we had previously, and where the data is coming from.
So I have a very naive question, maybe. Who was involved in the task groups who did the publication 103? So apparently none of us. Who was involved in the task group who did this? So probably, apparently none of us. If there are some people, I don't know. I think of, I don't know if Michaela Kreutzer was involved in the unscare evaluation of it. It was okay.
Dale Preston was there at the time of the calculation for the detriment was performed for cancer, at least by Dale Preston, for all cancer sites except skin and bone. And I asked him the question, what about heritable effects? Where there? It has been included in as a line in addition to your own calculation. We spend a lot of time trying to recalculate what has been done by Dale Preston in 2005 before the publication. I asked him about the heritable effect. His answer has been approximately, "Oh, don't ask me. It's a terrible mess. Don't ask me. I don't want to. I always refuse to be involved in the calculation of heritable effects." That's his position. I can ask him again, but clearly he was there at that time, and it has been done completely outside of him. At least he was not one of them. I expected some explanation of the final sum or so on, but clearly it was. His position is that it's something outside, something coming from space. Yeah. 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 Yes. I have to check that, but I don't think so. I think they apply the same.
Yeah, then that means that if we consider the evolution of the calculation of the health detriment for cancer, what does it mean? Do we have to add another weighting factors in the calculation for heritable effect or not? Or do we consider that it's fully separated, but then we have to justify what we have not the same treatment? Yeah. Yeah, but there is a weighting factor, but we don't. It's not directly related to the lethality. Also the weight of lethality, because and if we include some consideration on quality of life, how to do it for heritable effect? Do we have enough knowledge on that?
No, the risk for gonads, so heritable effects, is calculated as a nominal risk. So the 0.2 is the nominal risk. After that, you have a value for the lethality fraction, 0.8, non-fatal cancer weight, 0.82, and relative cancer-free life lost, 1.32, which is applied to this line of heritable effects. And the detriment is finally 25, which is rounded to 0.2 here on that slide. But the value for detriment is different from nominal risk, and there is some calculation from nominal risk. So what is provided by the N-scale report, the input in publication 103 is nominal risk. After that, there is some weighting. But I have to check if these weightings are coming from the same source, or I can ask Benora, she will know better than me, I think, I hope. I propose I try to look at that tonight, and we can come back to that tomorrow morning if I have news. If I don't, let's skip it. So that was part of the discussion. Many questions, not so many answers finally, but maybe the more I'm thinking about that, maybe Werner, what we should try to do is to try to calculate it in the same way, not to go in a complete revision of as TG 102, but at least to find somebody able to make sure that we understand precisely the different steps. So to take the equation, yeah, maybe we should try not only to try to understand it reading, but to go one step beyond, which is if we understand the parameters and we understand the baseline rates and so on, just to verify. I think Ludovic did it partly at least. Yeah. And as far as I remember, that's the reason why he found back that there was, in addition to what is written, the deadref coefficient of 3, which makes it not really 1 gray, but well, I don't remember how it applies, but something like that, yes. So we have to discuss it with him, but maybe it would be worthwhile to have something like that.
Yeah, check the origin of the data.
And that we understand the sequence, the sequence of calculation in the right way, including the severity factors, because I have to admit that I have to check.
Then do you consider that if we go ahead with the same equation, then we have to check if we are able to redo the calculation, identifying the origin of the data, and then based on that, we have a series of questions with regard to the possible evolution of knowledge, evolution of background data, and possibly question about the assumption which have been made and if we keep the same assumption or not. So we may have this first list, this first description of the calculation, and then the question to update, or if we want to make a new calculation in the future, what data are needed, and then we can interact with the other subgroup to check if, based on that, they have some modification to provide and say that the current classification is no more sufficient, or we need to add something, or then we have to consider, is it useful, is it manageable to add some element or not, because we have heard different evolution of the knowledge today, but not sure we can directly embark them into the calculation of the detriment. So, and then it should be justified why we already know that there are some evolution of the knowledge, but it's not sufficient to be, it's not useful for the calculation at this stage. It doesn't mean that in the future it could not be, but at this stage, it's we need to be able at the end to respond to all these questions.
And also, we all often also have the question, if we make some proposal of changes, if this proposal of changes is really justified, because any change we assume that means also changes in the operational radiation protection, and so I understand that some groups have some resistance if there are changes, so we have to justify them well.
Well, in ICRP 103, detriment was revised, and finally there was no impact at all on radiation limits or recommendations or on a operational point of view. But the results were not so different. 5.6 and 7.3. That's. No, sorry, 5.7 and 5.7, yes, instead of 7.3. So it was a decrease. The total detriment. Yeah. Other points? Maybe the paper that we have to write should be only on that. I think we have enough questions listed to make a paper already. So, but it was not the aim. But maybe a separated paper from that, to be able to reproduce the calculation and to list the issues that are open right now. So that's the shopping list.
Just found counterfactuals.
Yeah, so you found it. And in the equation, I don't know how they apply it.
Well, they just say.
They say with a dose rate reduction factor of 3 traditionally used.
And we don't change traditions. So that's something that will remain, that's clear. But what is the source about that? And clearly, if you look only at the equation as it is, you don't find it. So that's the reason why I think that Ludovic tried to reproduce it already, and he found that there was something wrong. And finally, he find this sentence and applying it. I don't remember where. Then in that case, it fits. But So again, it's not so easy. Everything is written, but maybe not in a way that everybody can repeat it on its own. So. No. Let's try to find somebody. Let's try to find somebody to do that. Are there also questions online? Frido?
No, thank you. I found the the sections in ICRP 103, and I will study them tonight. Maybe it will clarify some things. And it's the whole Annex A is full of it. But in particular, from A 205 onwards, if you want to look it up.
Geraldine, any comments or questions?
No, I don't think so. Thanks. It's been an interesting discussion. So no questions at the moment. Thank you.
Tomorrow the discussion will be more focused on application, so maybe more in the field.